All right. So today we're going to go ahead and we're going to do some review for exam 1. I'm going to be starting off with a review of aromaticity a little bit, and then we'll go on to substituents on an aromatic ring and how to deal with those. And then we'll finish off with some retrosynthesis in that area. Retrosynthesis involving like substituents and how to, figure out the order for adding them. So firstly, in terms of aromaticity, as you'll remember, we have aromatic compounds and anti-aromatic compounds. And so aromatic compounds will have they'll have 4 pi plus 2 pi electrons, or yeah. And anti-aromatic will just be like 4 pi electrons, right? And then also for both of them, you have to make sure that they're conjugated. That's for both of them. And so really in terms of the rest of them, sorry, sp2. In terms of the rest of the specifications, they're all the same for both of them. So you have to make sure that they're conjugated, that they are sp3, and that they are planar. Is that it? I feel like there's one more I'm missing. I don't know, maybe that's it. Oh yeah, cyclic. I'm spelling this wrong, right? Because it's like cycle. Yeah. Okay, so so these are the specifications for aromaticity and aromaticity. So if something doesn't fall into one of these, then we'll call it non-aromatic. So, for example, if it was instead of being cyclic, if it was simply a chain or something, acyclic, then we would call it non-aromatic. Okay, that's the other term we're looking for. Okay. So, in the questions from exam 1, you're going to have to classify things. You're going to have to figure out what belongs to what category. So I kind of want to just jump in because, like, you should remember most of this. I want to jump into some of the more specialized questions. And so those have to do with when there's usually like a cyclic compound that perhaps has some intercyclic things besides carbon. So this one is a ring, a 6-membered ring that has 2 oxygens in it. So what you're going to have to do is you're actually going to have to count the additional lone pairs. So in order for something to be aromatic, it doesn't necessarily need to have double bonds to contribute to the pi electrons. Lone pairs will also do it. So here we know that oxygen, because this is drawn as neutral, you can surmise that it has 4 lone pairs on each one, or 2 lone pairs on each oxygen. So what we do is we count each of the double bonds. So this is 1, and then this contributes as well. So that's 4 pi electrons so far, 5 pi electrons, and 8 pi electrons altogether. So 8 pi electrons. So this means that this one is what we'd call anti-aromatic. Okay, so that's for oxygen. If you see a bromide in the middle of a compound, then the bromide it wants to be attached to three things altogether. So in this situation, you can understand that it will have one lone pair, and that lone pair will contribute to aromaticity. So this is aromatic, right? But of course, since bromide likes to be attached to three things, if you see a bromide that's like this, so this is the same compound, but let's say that there's a double bond there and a double bond here. This one doesn't have a lone pair around it. And also, this is not conjugated because here's a single bond, here's a single bond, right? So, this one is non-aromatic.
Just a quick question. Is it bromide or boron?
Oh, sorry. Boron. Oh my god. Yeah. Bromide, of course, is Br, but this is B. Yeah, so boron. Thank you. So boron likes to be attached to three things. Nitrogen as well also likes to be attached to three things. So if you see a nitrogen, it's the same situation. If it's attached to two things, you know there's a lone pair. If it's attached to three things, you know there's no lone pair. And so essentially, if you see something like this oxygen up here, let's draw that again. So if you see an oxygen in this situation and you know that it has two lone pairs, only one of them will contribute to the aromaticity of the ring. So we call this one, again, anti-aromatic. Now, the other two lone pairs can be used to freely attach to hydrogens or disattach. And so if it has the availability of another lone pair that could possibly take on a hydrogen, so let's say if there was HBr, if it had a lone pair that could possibly take on an H from an acid, then we would call this a base. Of course, one that has the hydrogen, it's an acid, but before it takes on the hydrogen, it's a base. And so similarly, you know, if we had something like this, right? So looking at this question, we would say that this one is anti-aromatic, right? Because it has four lone pairs. Now, once that this nitrogen can let go of its hydrogen. So let's say it became the conjugate base of that, which looks like this, and it now has a lone pair. So this is now aromatic because it went from 4 pi to 4 pi plus 2. So at this point, we would consider this really aromatic. Now, this is like extremely acidic because in losing its hydrogen, it goes from very unstable to stable, right? Because aromaticity is way more stable than anything else. So because it's so desirable for it to lose its hydrogen, we would consider it extremely acidic. Okay. So one more note, a sulfur is going to behave the same exact way as an oxygen. So if we see a sulfur sitting like this, we know that it has two lone pairs. If we see it sitting like this, we know it has one lone pair, exactly like an oxygen. Okay. All right. So that's all I want to say about aromaticity, really. There's not much more to it. Make sure that it's cyclic. Make sure that it has, you know, it's conjugated. One thing is that if you have a situation like this one, when you have a nitrogen, you can think of it almost like a skip. So this is conjugated. So those nitrogens, those borons, those oxygens, those sulfurs, they almost act like skips inside of the ring. So it is considered a conjugated compound. Okay, let's move on to substituents of an aromatic ring. So to start off with, you have, so let's start off with our naming firstly. So you're going to have to remember the names of those 7 compounds in an aromatic ring. So of course, so to start off with, okay, I have to try to remember these. Okay, so there was a phenol, right? There was, there was, wait, toluene's like this, toluene. Then there was styrene, right? Am I correct?
Double bond at the top, but yes, styrene.
Oh yeah, there. Okay. Something looked off. And then we have, oh my god. Okay, I know that like after that we have, okay, so we have our benzoic acid. We have the benzaldehyde. Because that's just an aldehyde group, as we now know. And then we have one more that, what's this one? There's one more with a...
Is it acetophenone?
Oh yeah, acetophenone. And what is it, like a... What's on the other side?
Not, it's just another carbon. It's, yeah.
Oh,
Yeah.
yeah. Okay, so acetophenone. Okay, acetophenone. Okay, so, and then finally we just have our aniline and anisole. So this is aniline, NH2, and this is anisole. Wait, yeah, this one.
It's the weird one with the oxygen. That's really hard to remember. I think the other one was like benzyl alcohol, which is like the alcohol, but it's one carbon away from the benzene ring.
The benzoic acid?
No, benzyl alcohol.
Was that part of the thing we had to memorize though?
Yeah, it's on my list.
Oh, okay.
It's on the list I copied repeatedly, so I don't know. Either I memorized it by mistake or it's something we had to memorize.
No, I'm pretty sure we didn't have to know that. Let me just look at what it is just to make sure. No, well, I mean, I guess we could put it down in case, but it's not looking like something that I remember we had to learn. Okay, so this one is benzyl alcohol. Okay. So, but I know that for sure, like, I would always separate them out like this. Oh, this is aniline. So first you have, at the bottom, you have your anisole and aniline. They're easy to remember. So aniline is NH2, anisole is OCH3. And one of the ways that, like, that I think, JD, you brought this up. One cool way to memorize it is aniline has like another N in it. And anisole has like an O in it. So that just is what I use, honestly, to remember those. And then after that, we have our benzene ones, or like the ones that have like this very similar structure to each other. So the first one is benzoic acid, all the way on the left. That's just an acid, right? That's easy to recognize. Then we have benzaldehyde, that's just an aldehyde. Then we have acetophenone. Honestly, like, I haven't figured out a good way for knowing that. It's just, for me, it's the odd one out. Then at the top we have phenol. That's the OL is like gonna really help you. Toluene, it just is what it is, and styrene. So other than that, that's the benzyl alcohol. Just know that in case it comes up as well. So when you're doing your naming, what you're gonna do is you're gonna put, so like, for example, let's do an example. So here we have a benzaldehyde, right? So the benzaldehyde is our base. And meta to that, we have a Cl. So we're going to do M dash, so that stands for meta. And then we're going to have chloro benzaldehyde. Okay, so you first put the location for which the other thing is. So it's M-chloro benzaldehyde. And this one, so then if there was like multiple things coming off of it, so like if it was like a Cl and a Br, for example, and I've changed this to a benzoic acid, you would say M-chloro, P bromo, and then benzaldehyde, or it's benzoic acid. Okay, so you simply put the location right in front of the thing, and then at the very end, you're just going to put the basic structure of the aromatic ring. So I guess whenever you're naming an aromatic compound, you first want to look for like one of those eight, yeah, one of those 9 compounds that we mentioned above. You're going to want to look for one of those and then figure out how to name it. But yeah, so now that we've gone over naming, let's go on to something else, which is like, after that, we're gonna have to talk about what's, like, which one of these is, how activating are they, or how activating are different substituents on a aromatic ring, and then also position. So, I definitely, if you don't have the chart printed out, just go to the January 21st lecture, and there's a chapter 12 table there, which is the table you need to have and know. So what the table does is it lines out all of the different kinds of substituents off of an aromatic ring, from most strongly activating, right, to deactivating. So it's like a range. So it's like a range, and it kind of lists everything out. And for the, the standard kind of is hydrogen. It's the most like neutral. And then what happens is that what it tends to be is that the more activating ones are ortho and para directing, and the more deactivating ones tend to be meta directing. But the only exception that we have to that is we have our halogens, which are slightly deactivating. So X, they are deactivating, but they are ortho para directing. But other than that, the rest of them are meta directing in general. So some of the things that I've noticed about the trends is that if it attaches directly to a carbon, it's most definitely deactivating. So if it's like, deactivating. So if it attaches like this, and then there's a carbon here, no matter what else, if there's a carbon there, it's deactivating. And then also if it attaches directly to a sulfur, it is also even more deactivating. So here's how I line it up. So here's our carbon. Here's our sulfur. If it attaches directly to a sulfur, it's more deactivating than the carbons. And then finally, we have 2 very deactivating groups, which are CF3 and, oops, I said at the top, CF3 and NO2. So NO2 is the most deactivating. So that's kind of the trend that happens in the deactivating section. First, you start off with your ortho and para directing halogens. Then you go on to anything attached to a carbon, anything to attach to a sulfur, CF3, NO2. Okay, so let's go back up to the more activating substituents. So once we get past hydrogen, we're going to have, oh, there's one that I forgot about. Sorry, what I meant when I said, here, this is what I meant. If it's attached to a carbon with a carbonyl, attached to a sulfur with a carbonyl. Because of course, if it's attached to just like a carbon structure, like an alkyl structure, we would consider that to be activating, lightly activating, but still. So, in the activating portion, we have anything attached to a carbon. So I'll just change this to write like alkyl. So any kind of alkyl group, of course, like, you know, yeah, that kind of stuff. Even like a double bond, whatever. And then we also have, after that, all the things that attach to oxygens and nitrogens. So in general, we have, if it attaches to an oxygen at this point, it's going to be a little bit less activating than something that attaches to a nitrogen. And NH2 is the most activating thing. So I think that in general, like, these are really important ones to know. NH2, NO2, CF, halogens, and then just know the basics besides that. If it's attached to a carbon with a double bond O, if it's attached to a sulfur with a double bonded O, you know, so forth, so on. Yeah. So that's the basics of your chart, and this is going to be really important for determining like how to do your retrosynthesis. But before we go on to retrosynthesis, I want to talk about one more thing. So these are the questions he's going to ask you on the exam, where he shows you a ring, and it'll be aromatic, and it'll be like, here's compound X on this thing. So you have to determine what X is. And so this is a question that came from the exam. So 0.003. 0.001 and 0.004. So if you look at this, something interesting about these is that this one is definitely orthoparadirecting, right? Because it directs towards here and here mostly, and then this one is kind of left behind, right? So that's interesting. So it's orthoparadirecting. However, it's deactivating because it's like it's the numbers are so small, right? So these numbers are so small because, like, in reality, the range of these numbers can go all the way up to like 100, right? Because sometimes we see one where it's like, you know, 75 at the bottom or something, right? So in reality, we know that these numbers are really low, so it's deactivating. Of course, they'll never get to negative numbers. It's just the closer they are to zero, the more deactivating they are. So this is, you know, definitely deactivating. It's pretty close to zero. So yeah, so this is probably X is going to equal maybe like a Cl or a Br, something like that. It's a halogen. Okay? An F, an I, one of the following. Okay. So that's one of them. That's like more the easier one. Oh, by the way, 1 is the hydrogen. So if it's less than 1, it's deactivating. If it's more than 1, it's activating. So here's another example from the practice exam. So in this one, he has 4.5 times 10 to the negative 5. And here he has 67 times 10 to the negative 5. And then he has 7.5 times 10 to the negative 5. Okay, so the main point to take away from here is that it's definitely meta-directing. Since it's meta-directing, we know that it's going to be it's going to be deactivating, and honestly, pretty heavily deactivating. So here are the options that we're given. We're given CF, CF3. We're given CH3. We're given C, CH3, 3. We're given OCH3. We're given H, and we're given Br. So, of course, it's nothing activating. And so that would take this one off because it's less than 0. We know it's not activating. So if you look at this one, this is an alkyl group, and we listed alkyls right here. It's also not going to be this one because that's also an alkyl. This one is an oxygen, but it's not, so that's going to make it also activating because, look, we don't have anything in this range that attaches directly to an oxygen. So that takes this one, OCH3, off. Also, definitely not going to be hydrogen because hydrogen is neutral. Definitely not Br because it's meta-directing. So that would just leave us with CF. equals CF3. Okay, so that's just how you work through one of those questions. Let's go and move on to some more like applied situations for this. So in terms of applying the situations, we're first going to go over some regular problems involving like a situation where you're asked to attach something to a ring and then you have to figure out where it's going to go and stuff. So you'll get some regular reaction problems like this. So for example, let's see. All right, so here's one that I found from the practice exam. So this one involves two rings, and they are kind of attached to each other. This one has OCH3 on it, and then some methyls. So it also has this right here. So we have to kind of figure out, so this is reacting, this is, by the way, it's going to be bromination, Br2, Fe, Br3. So we have to figure out where is bromination going to occur. So bromination is going to occur wherever the bromide is drawn to. So you kind of first have to figure out who's the boss. So the candidates for boss, I guess, would be like this right here, this, and this. So obviously A, B, C, and D are all, A, C, and D are all the same. They're just alkyl groups. And alkyl groups are activating, but they're not as activating as group B. Because if we go back up to our list, we see that anything directly attached to an O is is more strongly activating than alkyl. So this is not good. Okay. So yeah. So B is definitely going to be the boss. And with that in mind, where is it going to direct? It's either going to be ortho or para. Well, both of the ortho positions are gone, so the bromine actually is going to go to the para in this case, for sure. So yeah, so that's just an example of how to attach these things. Here's another one. So in this one, we have NH2 and we have a methyl. So when looking at this one, and in this case, what's happening? Okay, so in this case, it's this and H2SO4. So this is a alkylation. So so basically, where is it gonna go? Well, it's gonna go to you have to figure out who the boss is. So again, NH2 is actually the boss here because NH2 is the highest, most activating thing possible. So NH2 is the boss definitely over that alkyl group. So yeah, so then where is it going to direct? Either ortho or para. Well, the para position is taken, so it's definitely going to go ortho. So the answer is going to be like this. We're going to keep our NH2 and our methyl in the exact same positions. And then what we're going to do is in the ortho position, we're just going to add the compound right there. So in case you can't remember, what's going to happen is that this is essentially going to take a hydrogen, right? The double bond is going to take a hydrogen because that's what double bonds do, especially in the presence of acid like that. And what that hydrogen is going to go, it's going to follow Markovnikov's rule. So hydrogen's going to end up in like, it's going to end up like this. This is just the mechanism. The hydrogen is going to end up on this end, to the end with the most hydrogens, and then we're left with a positive charge there. And so that's how it attacks the thing, and that's what you end up with. Okay, so that's an example of, I can't remember if this is alkylation or acylation. Do you guys remember?
Alkylation, I think.
Alkylation, yeah. Oh yeah, acylation is when it has a Cl. Okay, I remember now. Oh, you're the only one here now. That's funny. Okay. All right. So yeah, and then so that's the basics of how those questions work. You should definitely go through the exam looking for more of those. And then finally, we're gonna go on to some retrosynthesis. So for retrosynthesis, and JD, if you ever need to leave, that's fine. I'll just continue recording and just post it. Okay, so let's do a retrosynthesis problem with, I want to do it with an aromatic ring. So here's a problem where we start off with an aromatic ring, plain aromatic ring, and then we end up with aromatic ring, that thing. Okay, so what happens is that we're gonna have to figure out how to attach that alkyl group on, and then we're also going to have to change that. We're gonna have to add that D there. And for those of you who don't remember, it's gonna follow a Grignard thing. So first we need to have a BR MGBR in that position. So a BR is gonna have to develop across. This would have to be a BR right here. So I think that it makes sense to do acylation first. So for acylation, what is acylation? So acylation is basically, we're going to acylate this on, so it has a Cl on it. And what's the point of this? The point is that if I did an alkylation like before with with H3O plus, or sorry, HGSO4 or H3O plus, what would happen is that there would be not a rearrangement, but it wouldn't attach the way we want it to. So this would become this with the hydrogen at that end. So the positive charge would be here. And so we'd end up with the wrong thing. So if alkylation won't work for you, or if you just want to do acylation, that's fine. So in this situation, we're going to do acylation. And on the bottom, you'll do AlCl3. And what that does is it just attaches it the perfect way that we want it to. So that goes like that. Okay. So from this point, wait, that's too many. That's too many. Okay. Here we go. Okay. So from this point, we're going to have to do bromination. So we just do BR2, Fe, BR3. That will add a bromine across from it in that position. Change that Mg, Et2O, whatever. I like hate doing this. And then yeah. So then that will get us this, and that will be changed to a GBR. Then from there, all we have to do is do D2O, and that'll give us a D attached there. Okay. So yeah. I think we're done with this one. So basically what happens is that you just have to be careful of the idea that, well, okay, if you had attached the bromine there first, so let's take this and look at it a little bit closer. So if you had attached the bromine first, it would have been difficult to get acylation, or an acylation to that position, because bromine does do is very deactivating. So you have to take into account, is it how deactivating or activating is it, and also where will it prefer its the substituent to go. And so in this case, the bar here from doing BR first is not that BR would direct it to another area, it's just that it's not very activating to begin with. So that's definitely a less favorable solution that you would get points off for if you had done the BR first. Okay.
I mean, I think it's also worth thinking about like steric hindrance, because BR is much less sterically hindered than that R group.
Yeah.
So if you put in the really sterically hindered R group first, then the BR is less likely to go ortho, maybe. Possibly.
Yeah, that's true. Yeah, that's another good point. I completely forgot about that. You also do have to pay attention to stereohindrance a lot. So this group is definitely hindered. Ooh, okay. There we go. This group is definitely hindered compared to the BR, of course. So the thing is that if you have a very hindered group, it's going to promote the para position more. Like, so that helps it become like a much cleaner product. So when you go from this position and you add your BR, it's not, you're more likely to end up with it in your para position, like here, and it's less likely to become this, which is one of those, you know, nasty situations we don't want to end up with where we have such a mixture of things, right? This is not what we want. So yeah, so that's a point. Whereas bromine would kind of be all over the place with products everywhere. So I think something else worth going over is like let's go back to the beginning and kind of circle back at some things that I hinted about, such as Grignard. We're going to talk about Grignard. We're going to talk about MBS, acylation, alkylation, bromination, all that kind of stuff. Just reactions in general. So in terms of MBS, what does MBS do? MBS is just going to add bromine to the most favorable position. So this is kind of the example that, you know, is very like characteristic to give just to teach this. So with MBS, you have to figure out which one's the most stable position that it could go to where it's benzylic. So that means that this branch is like off limits kind of, because it can't really attach onto there. That would break octet. So it would either be able to go here or here. And between the two, this one is definitely the best. So this would be the solution, BR. It would go there. So that's how MBS works. Bromination, we already talked about that. So for bromination, you're just simply, you do BR2 and then FeBr3. You could also do it with Cl. You could do Cl2, FeCl, or Fe, is it Fe still? Cl2. I don't know. It seems a little bit wrong to say FeCl3, but perhaps. I don't know. But anyways, so that's how you attach a halogen. And then for acylation, like we talked about, so the benefit of acylation is that you could really just attach anything with like a Cl or something on it. So essentially what you can have is, again, like the situation we pointed out above. So let's say this was a BR and I want to end up with like something that is like primary, like that. I don't know. So in this situation, you can't just take this with a double bond and attach it. That would not work because it would be more likely to attach. Oops. I'm just going to change this a little bit. Yeah. So it wouldn't really attach the right way. It would end up more like this. So for that reason, we're going to choose acylation. And so for acylation, all you do is you just put the whole thing that you want, and you just put a Cl at the end. Yeah. And then AlCl3 is important as well.
I'm so confused. Doesn't acylation contain like a carbonyl group?
Maybe I'm using the wrong word, but
am I confusing it? Because I have alkylation and acylation, where alkylation is one where it just rearranges even if there's like a Cl at the end, and acylation puts a ketone in like the benzylic position, and then you can just use like the Clemmensen reduction.
Oh my god, yeah. This is just alkylation, right? And
yeah, that's rearrange. Just alkylation. And I think it would probably rearrange.
Yeah, somehow. It would rearrange. It would. Okay. All right, yeah. That was definitely a mistake. So this is alkylation because you're adding an alkyl, and acyl is a double bonded O that is attached to carbons. So yeah, in this situation, I actually don't really know if we have a way, now that I think about it, I don't really know if we have a way of attaching like a chain like that. I don't think it could happen. So yeah, so alkylation can work in a few ways. We can have like our Cl here, and that would give us like that. Or you could just do it with a double bond as well. That's a possibility. And then for acylation, what acylation really is I've been using the word incorrectly. It's if we had the same situation, let's just give us a BR, and what we do is we have a double bond, so it can have a Cl here. It could have other things. We'll go over that in a second. But what it does is it just attaches that with a double bond on it. So that's kind of the marker of acylation, that the double bonded O ends up there. And so we get this. And so another example of how to do that, it doesn't necessarily need to be a Cl in that position. I'll just show you the other ways you could draw it. It could be this. So you could leave it like that. I can't really think of, is there another way of doing it?
I mean, there's an anhydride, I think. My notes
Like,
say anhydride. Like,
ring.
what
Oh,
you
yeah,
have.
Yeah,
with 2 of the carbonyls.
Yeah. But that's just gonna end up being the same situation. So it could have like another carbonyl there, but mainly your oxygen, it does need to attach to something else. Of course, it could be like, yeah, I think that's the main 2 ways of doing it. So, so that's alkylation and acylation, and we did a bromination. So what else do we have? So then, of course, we have that method. Just keep that in mind with a double bond. And then here is a cuprid reaction, I think it's called. So for the cuprid reactions, let's say that you have, so this is OTS, or maybe not OTS in this position, but yeah. No, it is OTS. So we have OTS right here. And what happens is that if there's any kind of good group, so it definitely doesn't need to be OTS, just a good living group. And we can react that with something like this, maybe. CULI. There's 2 of them though. So what that does is it simply protonates the good leaving group and attaches whatever is inside of the bracket, just one of them though. So this is equivalent to this being attached. Okay. So I think this might be your best bet of adding like a chain to a aromatic ring, to go with a cuprid reaction. So what this is going to do is this is going to protonate right there. So we get aromatic ring, and then attached to it, we're going to have 1, 2, or it might rearrange. I'm not sure.
In this case, I'm not sure it will, but just to clarify, you can put OTS in place of an OH using TSCl, correct?
Not TSCl. You would write it like this. TSCl is before it attaches there.
Yeah, so if I had an OH and I wanted to make it OTS, would I use TSCl?
Yes.
Or
if you have some other leaving group. It doesn't have to be like anything in particular, because that one would just look like Cl and then S, right?
Right. I sort of don't remember that from Orgo 1, so just wanted to make sure.
So that's TSCl, and it has to have a good leaving group, and it will protonate and replace that other good leaving group. But yeah, so once it's on there, it's OTS, and then before it's on is TSCl. And either way, it's just a good leaving group, a really good leaving group. So what mass won't really use that much. It definitely won't come up. So I'm not sure if the cuprid has a rearrangement. I think it does. Now that I think about it, I think it does. Like, I don't know. I just have this feeling that it does. Maybe your best bet if you need a chain coming off would be some Grignard or something. Because I do think the cuprid rearranges.
I mean, the cuprid is also like an organometallic, so I really don't see any reason to use one over the other.
Compared to the Grignard?
Yeah, because they're in the same section. They're both in chapter 14.
Yeah, but if you use the Grignard, you could eventually get rid of the carbonyl and have like no rearrangement essentially. I think.
Okay.
I think it might be a little bit easier to end up. I don't know. I'm having a little bit of trouble. You just have to go through your retrosynthesis and find out what to do if you want to attach a chain. If you figure it out, JD, just let me know or send it in the chat or something. Because
It
I'm
looks
pretty
like
sure
you can just if you have like something that has like a chlorine on the end and you have like a cupric, you can just plug a chain on with the cupric. But I think the leaving group also has to be a good leaving group. I guess OTS would work.
Yeah, OTS would probably work. So you're saying cuprid does not have rearrangement.
According to my notes, cupric does not rearrange.
Okay, that might be helpful because I know there was a way, and this one might be it. Okay. So if it doesn't rearrange, this is what we'd end up with. So right now we're going with the assumption that it doesn't rearrange. Of course, this isn't, this is just like suggestions for how to study, really. It's not like the last word on the topic. Okay. So with that, we've gone over okay. So, and then the Grignard, like you should remember that fairly well because we've done Grignard recently too, right? Grignard, you just have something with like an MGDR on it. And then you just react it with something that has like a double bonded O on it. So it could be like this, for example, and what you get is the attachment that you would imagine if it attached from that direction. That's one extra. Yeah. So that's essentially the answer we'd get if we did that Grignard. And then of course, like the way to attach GTO, we just talked about that. All right. What else do we have? There's a lot of acylation here. Okay. So like another example of Grignard is this one. I really like these questions. So we have here a situation where this is reacting with 2 moles of this. And so if we have 2 moles, we're going to have to assume that they both attack. So what happens is that the first one attacks, or actually it would look like this. The one attacks, and then that breaks this off, and then the second one attacks. Okay. So what we end up with is when the first one attacks, here, let me draw it out first. Okay. So when the first one attacks, what happens is that we end up with a break in this bond. So that bond is essentially gone. And this automatically will pick up an OH in solution. And what we have is one of those attached. Then when the second one attacks, this comes up. So because to, keep octet, now it's just attached by one bond. And so that will automatically take up an OH and the other one will be attached. So that's how to do that problem. Let's see. Okay. So this one's important. CH2, I2, ZN. Okay, so this one is a problem for the practice exam again. So he has this, and we're reacting it with CH2, I2, zinc, Cu, ET2O, And what this does is it just makes a triangle. This is much different than epoxidation. Just keep that in mind. It just turns it into a completely alkyl type triangle. So make sure you don't end up just assuming it's this thing. That's a later exam. That's our last exam that we just took. All right. Okay, I think that pretty much sums up everything that we do in this exam, in terms of, that. Let's go back to a couple of things. Okay, so here's one question where he'll ask you, what are the reagents that created a product? So the product in question, and he'll tell you it's Grignard. So the product in question is like this. Okay, so what kind of products do you envision could have gone towards this? Well, there's honestly so many different routes to take with this question. But you just have to envision one that's going to be a carbonyl compound and one that's going to be the Grignard reagent, which is the one that has the MGBR. So honestly, my first go at it, I would see like this. I don't know, for me, that's just, maybe something like this. And actually, no, it wouldn't have a hydrogen. Maybe something like this. Okay. And also it would have two of these. Okay. So those would simply attack. The first one would break that off, and then the other one would do that. So that's one of the combos that you could do. Another combo that you could do, let's move this up. Okay. Another combo you could do would be attaching the, it could be like this. You could have like this, and then plus one of those. That's another option. Another option is, I think those are all the options for it being there. So this is just going to take a lot of thinking, but obviously quick. But just make sure that what you write makes sense. So you could put the MGBR here and leave this as this. What else? I think there's definitely, I think, more options. I just can't really think of them right now. I mean, of course, you could always just do the same one up here. Sorry, just a second. You could just do this with the CL as well. Like, that's just, same thing. There's always so many options. What do you say, JD?
No, I was just about to say you covered most of the ones I can think of, I think.
Yeah.
Like, I can't think of anything else.
Yeah. Honestly, like, as long as you can think of one that works, that's fine. As if you sit there longer, you'll probably figure out more. I don't know. Okay, so there's that question I want to remind you of. You have to be used to solving these type of puzzles. Then there's the question of which one is the most stable, which I definitely have to go over in terms of reactivity. So what he did was he listed a whole bunch of these. So four of them. And this one has a BR, NO2, OCH3, and this one's just nothing. Okay, so the question is, which one is going to be nitrated most easily? So which one is going to be nitrated most easily? So what that means is that we essentially have to list them in terms of which one is going to be like the most activating to least activating. So the most activating would be number 3. Yeah, number 3. So, or sorry, yeah, this one. So this would be number 1, the most activating. The second most activating would be the neutral one, this one. And then probably BR, right? And then finally NO2. So this is just how to list them in terms of how reactive it would be with, being substituted onto, nitration or something. Okay, is there anything else? We're actually nearing the end of most of the material that we need to cover. Okay. So yeah, I think that's pretty much it for today. Jay, do you have any other questions or anything?
Nope, I'm just looking through my notes. Did we talk about Clemenson yet?
Yeah, Clemenson. So what does Clemenson do? It simply removes a carbonyl. So if you have something like this, if you do Clemenson, you can get this. So what I was saying in terms of how do you attach a chain to your aromatic ring, this is probably my preferred method, to go through a Grignard and then do Clemenson. We also know a few other methods of doing this from later on, like in terms of, we know how to do like maybe like with Jones and PCC. There are other methods of doing stuff that's similar.
Right,
But
and like NABH4.
yeah, so Clemenson just does that. Another thing that I think I mean, it would be really like weird to, I mean, it would be really weird if you don't know this, but I'll just say it just in case. When you have something that has like this, just remember your good old like LAH, I think this might be the next exam, LAH and NABH, where I want to say.
Yeah,
This is all.
NABH4. It's exam 2.
That's exam 2, yeah. Yeah, that's true. Okay, so yeah, that wasn't really relevant this time, but yeah, so just know that though. But otherwise, I think we're done. So we covered aromaticity and then all the substitutions that can happen to aromaticity, and then just some other little reactions that are related really to aromaticity. So everything about this exam is just aromaticity, essentially. And just remember your naming, and definitely try to go over this quick little chart that I drew. Honestly, this is all you need to memorize. Like, whenever you see like a chart like in Orgo, you should really try to simplify it down as much as possible so that you understand it. So whatever works for you, just make sure you memorize it before the exam, because it's going to be critical to know this stuff. And I think that's it for today then. So I'm gonna go ahead and end the recording.